Okay, so hi everyone. Today I will present a work which was published in TPDS 18, the cache-oblivious MPI outward communication based on Morton order. So the main idea is how to implement MPI outward collective communication efficiently on shared memory machine, but we also extend the algorithm to distributed multi-node machine. I will go to the details later in the following slides. So everyone here is very familiar with MPI collective operation. I will not go into the detail for this. So the all-to-all collective operation we focus in this work include MPI all-to-all and MPI all-gather. For MPI all-to-all, each process will send a data block to a destination process, and the overall MPI all-to-all performs like a matrix transpose, but in a data block-wise way. And for MPI all-gather, each process will gather all the data from all the other processes, send the buffer, and put it in its receive buffer. So commonly for MPI collective operation, each operation may have several different algorithms. For example, for MPI all-gather, it has Brook algorithm, recursive doubling, and the ring algorithm for large message sets. And the same for MPI all-to-all. In the communication library, it will select the best algorithm according to the number of processes and the message sets, and try to minimize the latency and the bandwidth overhead over the interconnected network. So the existing algorithm is mainly designed and optimized for interconnected network, but how to efficiently implement collective on shared memory. So on shared memory on single compute node, it may have many cores intranode. For example, for Intel Xeon Phi, it has 16 cores, and for Intel Xeon E7-8890, it has 72 cores. And these many core architectures also have deep memory hierarchy. For example, L1, L2 as caches, and the DRAM. And they also have various memory arrangements. For Intel Xeon Phi, it has unified memory access pattern, the NUMA, and for Intel Xeon E7, it has NUMA architecture. And they have networks on chip with hardware cache coherence protocol. And the data transfer between cores on chip is largely affected by cache coherence protocol. So how to efficiently utilize the hardware cache and maximize the performance of collective communication on this shared memory many core architecture is the motivation of this work. So our algorithm is implemented based on shared heap. So on the left figure is show the traditional MPI implementation for the processes within a single compute node. The source process will copy the send buffer into shared memory segment, and the destination process will then copy the data out from the shared memory segment. In our implementation, we use shared heap, namely all the processes within a compute node will share the heap space. So in this way, each process intranode can directly access all the send buffers and the receive buffers of the other processes within a single compute node. So in this way, it will bring us more opportunity to optimize the data locality and even design cache-oblivious algorithm for the all-to-all collective operations. So here is how to efficiently implement MPI all-to-all on shared memory. In this example, we use 8 processes, and suppose all the processes share a heap space, and the send buffers, all the send buffers of these processes forms a send buffer matrix, and the same for receive buffers. Each element of the matrix is a data block used in MPI auto operation. So in the naive implementation, each process will copy a column of a send buffer matrix into its receive buffer. So as we can see in this way, because the column of the send buffer is not consecutive, namely it has bad data locality. So what we do here is to use Morton order to get the order of data copying. And this Morton order will form a Z-shaped curve. And the Z-shaped curve is equally partitioned into P processes, P segments, and each process will handle a single segment. So in this way, we can see the data locality, the spatial locality of both send buffer matrix and the receive buffer matrix is exploited. And this is the implementation for MPI altogether. So similarly, all the 8 processes share a heap space, and all the send buffers of the processes will form a send buffer vector. We treat it as a vector. And in the naive implementation, each process will copy the data from the send buffer vector into its own receive buffer. However, in this way, the temporal locality within this send buffer is not exploited. So similarly, we also use the Morton order to get the data block copying from the send buffer vector into the receive buffer matrix. Take process 0 as an example. It will handle the first segment of the Z-shaped curve. First, process 0 will copy A0, B0 into its receive buffer. And then it will reuse the data block A0 and B0 and copy it into the receive buffer of process 1. So in this way, the data block A0 and B0 are reused, so the temporal locality of send buffer vector is exploited. Next is how to deal with the case if the number of processes is non-power of 2. So as shown in the previous example, we use 8 processes as an example, which is a power of 2. However, if we use the same method to generate the Morton order for the case of non-power of 2 processes, for example, in this example, we have 5 processes. It may lead to on the edge of this matrix, the edge element may have bad locality. So alternatively, in our implementation for this non-power of 2 processes, we use binary search algorithm to generate a more balanced curve. So in the implementation, if the number of process P is a non-power of 2, the Morton order is generated with the creation of the communicator structure. And the collective operations on the same communicator will reuse the Morton order. But if the process is power of 2, the Morton order can be efficiently generated on the fly using high performance bit manipulated instructions. Next, we analyze the cache complexity for our implementation. So here we assume an ideal distributed cache model. For each core, it has a private cache, and Z is the cache capacity, and L is the cache line length, and Q is the number of cache misses caused by incurred by a specific operation, namely the cache complexity of the operation. And we assume the cache line replacement strategy is optimal. Then we present the cache complexity for the naive implementation and the Morton outer-based implementation for MPI all-to-all on shared memory. So we can prove that the cache complexity for Morton order-based all-to-all implementation is asymptotically optimal in terms of cache complexity. And also in our algorithm, we do not involve any parameter related to the hardware cache. So this means our Morton order-based algorithm is cache-oblivious. So for the detailed analysis for the cache complexity, please refer to our paper. So by compare the cache complexity of the naive implementation and our cache-oblivious implementation, we can see the smaller the value of the data block size B, the larger advantage of our cache-oblivious algorithm. Next is the cache complexity analysis for MPI algorithm. Similarly, we can prove that our cache-oblivious implementation it has the same cache complexity as any cache-aware algorithm which use tiling as the optimization strategy. And compared with the naive implementation, our implementation has a lower number of cache misses if the block size is less than half of the cache capacity. We further apply our algorithm to neighborhood collective operation. For neighborhood collective operation, it has a sparse communication pattern. So here we use 9 processes as an example, which are arranged in 2D Cartesian topology. On the left matrix, it shows the communication demand matrix of the collective operation. And then we generate the Z-shaped curve using Morton order on this demand matrix. After that, we remove the idle element, namely the element which do not have any communication from the demand matrix, and only keep the element with communication. This will form a compact curve, and the communication involved in the neighborhood collective operation is happened according to the order of the compact curve. In this way, the data locality in neighborhood collective operation is also exploited. And next, we further optimize the algorithm for NUMA architectures. So here is an example of a NUMA architecture which has 4 NUMA nodes, and each NUMA node has 4 cores. So namely, we have 16 cores and all 16 processes. So if we use the same method as discussed previously to generate the Morton order and get the communication schedule using the Morton order, it will ignore the NUMA architecture, which may lead to some process copy the data from one remote NUMA node into another remote NUMA node. So this will seriously jeopardize the performance. So what we do here is to optimize the algorithm for the NUMA architecture a little bit. So each process within a NUMA node, it will in turn read the data from another NUMA node one by one. So in this way, it can guarantee that the receive buffer is only accessed on the local NUMA node, and all the process within a NUMA node still copy the data following the Morton order. So this means our algorithm is still cache oblivious within each NUMA node. However, overall, the algorithm is NUMA aware. We also extend our algorithm to multi-node distributed machine. So here we model the architecture of distributed machine similar to the ideal distributed cache model. So in the model, the DRAM of each node is considered as a private cache, and all the compute nodes are connected through the interconnected network. And in the model, we treat the interconnected network as a black box, namely, we do not consider the network topology, process placement method, and also the routing strategy. So we only keep the function that each pair of undernodes can exchange message through the interconnected network. So for the internode communication involved in the outward collective operation, it also carried out following the modern order. And also, since there is no hardware cache for distributed memory machine, the remote cache is prefetched manually by message aggregation. So here is an example for MPI auto with 8 compute nodes from the point of view of process 0. Following the Morton order, process 0 will receive the data from the remote node from P1, P2, and P3 simultaneously. And then it will do a local transpose on its own DRAM. After that, P0 will send out the message to the destination processes simultaneously. Next, we analyze the cache complexity for different implementations on multi-node machines, including our cache-oblivious algorithm, the Brooks algorithm, I send, I receive, and wait all, and pairwise exchange algorithm. So in the formula, I is the size of receive or send buffer. P is the number of processes. So here we compare it with Brooks algorithm. Our algorithm has less communication volume. And also we have higher communication parallelism. This is because after the local transpose on the DRAM, each process can simultaneously send out the message to the destination processes. And compared with the I send, I receive wait all, and pairwise exchange algorithm, our algorithm incurs less number of messages. For the evaluation, we conducted the environment on 3 different parallel architectures. First is a single NUMA machine, Xeon Phi, which has 16 cores, and a single NUMA machine, Xeon E7, which has 72 cores, and a multi-node machine, which has 256 nodes connected by InfiniBand. Next, I briefly introduce the abbreviations used in the following figure. So SH naive is the naive implementation based on shared heap, and SHCO is our cache-oblivious algorithm based on shared heap. SH NUMA CO denotes the cache-oblivious algorithm optimized for NUMA architecture, and MNCO is the algorithm applied, the cache-oblivious algorithm applied on multi-node machines. So this figure shows the latency result for on Xeon Phi, which is a NUMA machine. So we compare our implementation with the traditional MPI implementations, including MPIG, MVPIG2, Intel MPI, and MVPIG2 optimized for the Intel Xeon architecture. So compared all the traditional MPI implementation, our algorithm have performance advantage. This is because we both use shared heap as the underlying data transfer mechanism, and also we highly efficient utilize the cache. And compared with the SH naive, our algorithm has a performance advantage for small and medium message size. The reason is this is consistent with our cache complexity analysis previously. And this figure shows the result on Intel Xeon E7, which is a NUMA machine. From the figure, it shows that SH NUMA CO outperforms the naive implementation for small and medium message sets, which is also consistent with our cache complexity analysis. However, we can see the fully cache-oblivious algorithm SHCO performs worse than the SH NUMA CO. This is because for the fully cache-oblivious algorithm, it ignores the NUMA architecture, which may lead to too many remote memory accesses. And next, we also measure and compare the number of cache misses on a NUMA machine for different implementations of MPI algorithm. This NUMA machine has L1, L2, and L3 cache. We can see for SH NUMA CO, it has lower L1 and L2 cache misses than the naive implementation. This is because we better exploit the data locality in our cache-oblivious algorithm. On the L3 cache, we can see the SHCO, which is a fully cache-oblivious algorithm. It has higher L3 cache misses than both SH NUMA CO and SH naive. This is again because it ignores the NUMA architecture, and it may cause too many remote cache miss. This is the result on multi-node machine. We compare our implementation with MPI NYPG2. The results show that our algorithm outperforms NYPG2 by about one-fold on average for small message sizes. So the reason is that compared with the Brook algorithm, which is used in NYPG2 for small message size, our algorithm has less communication volume, and also we have higher communication parallelism. So here we are not proposing to replace all the existing algorithm by our algorithm, but we proposing an algorithm alternative which may have performance advantage for a specific range of message sets and number of processes. So at last, I conclude this work. We implement the shared memory auto collective based on Morton order, and we analyze the cache complexity on shared memory and prove that our implementation is cache oblivious. And we further apply the algorithm to neighborhood collective operation and optimize it for NUMA architecture and extend the algorithm to distributed machines. Evaluations on different parallel architectures show the performance advantage of our algorithm. So for more details and information, please to refer to our paper here. And that's all for my presentation. Any questions?